Welcome to the last lecture of the course. And today it will be relatively quick, especially if you don't have any questions about any part of the course. So the program of today will be first, I will give you an example of what are the parts to identify in a scientific paper using the paper that I shared with you at the end of the last lecture. That will give you an example of a comment that I made about it. Then I will I will show you a possibility on the last topic of image analysis, which is image segmentation. We won't run that as it's, I didn't find a way which you can run on limited computational resources, so I've made a pre-made notebook that you can go through. And finally, I will detail the possibilities of dataset that I will share with you on request for the exam project. So, now let's start with the first topic, which is the analysis of the paper that I shared with you at the end of the last lecture. And this is the title. And all the bibliographical information about the paper itself. So, after reading this paper, one should be able to first understand well the background and the clinical problem. And so this, in my opinion, was a paper made relatively well in the way it was written and exposed. Let's say more than on the algorithm itself is nothing novel or particularly extraordinary, but it's really well written in the different section. So it's clear what they're doing. They introduced the concept of sarcopenia, which is the loss of muscle mass, which is an especially indicator of poor or very poor prognosis in patients with lung cancers. And by convention, the most standardized metrics that there is to quantify sarcopenia is a manual measuring on CT images at the level of a lumbar vertebra. However, when one is monitoring lung cancer with CT, one acquires exclusively the thorax. What they aim to do with this paper is quite well stated, and it's to perform a radiomics analysis of the muscles at the level of a thorax vertebra, which instead will be present in the acquisition, and use that to predict whether sarcopenia is present or not as a binary outcome. Now, I've listed you some questions that many are generic and some are specific to this paper, on which you need to reflect about this paper, and in this case it was are they describing well enough the inclusion criteria? Are the imaging procedures described well enough so you can replicate them? If the research question is clearly stated, given that they're predicting something, if the gold standard is clearly defined, and finally the radiomics extraction, and how did they, given that they were working with radiomics, how did they do that? Now, part is pretty easy. Are the inclusion criteria well described? Well, absolutely, for sure. Here they say that they're using consecutive patients. They had some pretty clearly defined inclusion criteria, which are pretty standard. And the exclusion criteria were presence of other very poor condition like presence of metastases or some technical factors, so nothing to complain about. And then they state that they split the data set randomly, so this is extremely straightforward. The next question was about the imaging procedures, and here it's everything they say about this. This is just very few lines, but it's everything actually one needs to know. One can see a limit might be the fact that this is a single center retrospective study, so maybe the generalizability with on other kinds of imaging or other protocols, because this is a very precise protocol, with especially with low-dose CT. So whether this generalizes to high-dose data to other models, kind of image reconstruction and so on, is something that they will not analyze. But anyway, this is very complete. More interesting, it's how is the gold, what is the research question and how is the gold standard defined? Now, the research question is to be able to predict the presence of sarcopenia from T12 CT, so, which is the vertebra, the thorax vertebra, from T12 CT images. And they want to predict it as a binary outcome, which is either present or not present. And the gold standard is the using the state-of-the-art procedure, which is a manual analysis over the lumbar vertebra range. An interesting fact that they did, procedures that they did, is a robustness analysis. So even on the gold standard, they asked which is a manual procedure, they asked the human raters to do it twice blindly with some weeks of time distance between the two analyses. So this gives us some idea on how well defined our gold standard is, which is, especially in medicine, is something quite often not that clear. Now, if anything, one comment that I might have on this is that they take a continuous measure and then they binarize it and they say, over this threshold, this is, over this threshold, it's this pathology is present, under it's not present, while they could have kept the continuous values and try to fit that. Now, as they are doing a radiomics analysis and one wants to be able to replicate that, the point of scientific publication is to allow people to replicate your analysis. Here they give all the data. They described which library they used, which was Radiomics. They described that they worked on single slice CT, which regions of interest they used, and it is a semi, here I've written semi-manual. It's a kind of, it was a procedures which started from an automatic segmentation done with just thresholding on intensity, on Hounsfield intensity values and with manual definition. And they describe all the, in detail all the steps that they use for intensity and voxel size normalization, which again is very short, but given that is completely arbitrary, which setting do you use, it's good that I've written it. Now, here I had two questions about the results section. We have one. First one is that here they performed, this is something that they very often do in, the physicians do. They take a sample of subjects, they split it randomly in, like in two in this case, and then they run descriptive statistics of the two data sets. And sometimes they get significantly different in the statistical sense properties, which from a statistical point of view, it's a very curious finding, because if you run random subsampling, everything should be equal within the statistical range. Most likely. So theoretically, it's not even, it doesn't really make sense to perform this statistical test. I mean, it was different if you had acquired two groups of patients into hospitals and found that the mean age of the patient, it was different. But in this case, it's a single data set that they've split, so why would you run a statistical test? Now, in this case, the percentage, the gender representation in the two data sets might be a statistical, how can you call it, a statistical fluke, because we are working only with 6 and 24. So, and physicians like to work with these 0.05 statistical thresholds. So, out of chance, you actually get sometimes things that are that have some kind of small value like that. On the first finding related to the age, it might be that the fact that the subjects have very non-normal distribution. So if you are working with relatively small data sets, which, as you can see, span a very wide age range, then you might end up with this artifactual, very high statistical significance between two groups that are not, by definition, not different. Now, the question is about, do you have all the data you need to evaluate the proposed algorithm? In this case, this is pretty clearly yes, because they're reporting lots, all the metrics that you can imagine that you can generally use to evaluate a binary classifier. They have the confusion matrix. They have ROC curves, both on both data sets. So it's so there is no issue about that here. Now, oops. Sorry. Here are some more open-ended questions. As we said, the discussion section of a paper is by definition open-ended, is a commentary done by the authors on their finding. And here's the place where some people, where you who are reading the paper should ask yourself, is everything they did correct? So, of course, the first question is, why isn't the abdominal CT acquired for lung cancer patients? Well, because it's not necessary and it requires quite a large radiation dose. About the fairness of their results, here, well, this is a very tricky question because it depends what you mean by fair. Of course, they are saying that their algorithm works really, really well, and I mean, the classification's performance is a 90% accuracy, however you define it, because it's pretty consistent amongst different metrics, is for sure good. Now, but however, here you get many more questions, so it's, one could ask yourself first, how would have the performance been if you tried to fit a regression between your continuous value of the gold standard of this SME metric and what you can acquire using radiomics? Then, for sure, a question that often people who are new to artificial intelligence, especially, physicians, say, okay, algorithms do artificial intelligence on that because it's not clear to them what you're doing. And in this case, they are analyzing a slice of a CT which actually is just 2 centimeters away from the other and which is still showing some of the, let's call them the core muscles of the body, the abdominal and some muscles on the spine. So it's not like they're analyzing data at the beginning of the chest. And probably they could have run a very simple linear regression between the percentage of muscle area on this slice, which was just 3 centimeters away, and run a linear regression, and you should have used that as a baseline for comparison to see whether your advanced analysis works better. Remember that the most important part when you're inventing some kind of algorithms is, well, for didactic purposes, you might want to try any algorithm, but if you want to go in the production, put a product on the market, your algorithm needs to have a justification. I mean, why do you want a 10 million parameters model if a linear regression works as well? A linear regression is much more explainable. You're sure that it's going to be free from many kinds of biases, not all possible biases, but so the reference standards should also always be present, and it's very often arbitrary how to choose your baseline. Okay, any question about that? Okay, concerning image segmentation instead, I just want to show you a notebook that I've uploaded on your drive to show how you can segment with a very basic network the Bratz dataset. I will comment, so if you have the Bratz dataset locally, and if you want to run it, if you have GPU resources, you can use it. And I just wanted to comment on some programming choice that I made to process that. So the first things to keep in mind, we already worked on that with the radiomics experience at the beginning of the course. We have 4 images available, all of which contain complementary information, because we have the T1 image, the T1 with contrast enhancement, the flare image, and the T2 image. And each finding is visible on a different image channel. So the comparison between the flare image and the T2 image allow us to see the so-called edema, which is the region full of water recruited from inflammation. The comparison between the T1 and the T1 with contrast image allow us to see these the regions with contrast enhancement. So it's good to use all of them. And indeed, to read the data, I have decided to put them in this kind of structure, which has generally, we take in Python, and especially in Keras, in PyTorch, the first index with the number of with the subject index, then the whole 3D volume, and I use the 4 MR images as they were 4 different channels. Well, not as they were, as different channels, because that's what they are. Then, well, during the reading and downsampling the images by 2 by 2 by 2 millimeter instead of 1 by 1 by 1 for better computational performances. If you have computational resources, it's better to keep the full resolution. And I'm just doing a resampling when reading. And then a topic which I like to stress a lot, we have we need to scale the images. MR images, all of them have random, non-meaningful intensity values, so we need to scale them for better conditioning to a common scale. Now remember that in this case we will build well, a neural network, but it could have been anything, which takes in input an image, and in output it gives us a categorical output. So you can, if you're using a neural network, this neural network might work by its, theoretically it should be able to learn by itself the optimal scaling, but if you start by bringing the images to a common range, it will make the learning much, much easier, especially when the images are spanning 4 orders of magnitudes between different patients. If they were spanning a range of 2, probably you could have skipped that. So the other things that I did, training and splitting the data set, was to, where is the reshaping? Oh, OK. Now I'm splitting the data set, and I'm deciding next to work on a slice-by-slice basis. I'm not using the full volume to save memory. Now, things that you need to really care a lot when you're doing the data splitting is to first split the data set according to the patient label, and then to reshape them into the volumes. Because if you first stack all the volumes as a stack of slices, and then you do the random splitting, you get images from the same patient in both the training and the validation data set. And this is something that we commented on even when working on the FDA process for approval of medical devices, that images from the same patient, different slices are independent in terms of noise and other things, but they still are correlated. They contain a number of overlapping information. So you need to make sure that they are training and testing data set do not contain the same patient. Now, what we are doing here is just to build a very standard neural network. A very standard UNet, the one with the skip connections. So for every layer in the max pooling layer, at every resolution in the decoder part of the UNet, we are just concatenating with the layer at the same resolution, which, if you remember, is something that we skipped in the autoencoder experience, because in the autoencoder, you don't want to preserve high-level features. You want to really contract all the representation should pass through the bottleneck. Here, instead, you want to skip the bottleneck as much as possible. Here we see the summary of the network. This is a relatively light network with only 600,000 parameters. Well, it's not really only is something that I might say when working with 60,000, but it's much smaller than networks with 20 million parameters, which are state of the art. Now, finally, we define the metrics. One metrics that we can have is the dice accuracy, which is the extension to images, if you want, of the intersection over union metric. It's pretty standard, and then we can just define the model. Now, as a loss, we should use the categorical cross entropy. We have 4 different possible categories because our segmentation is multi-label. And okay, that's it. Now, a trick that I'm not sure if you've seen, when we want to segment in 4 possible exclusive categories. So the labels are only one label is true at the time. So generally, what you do is to use the softmax activation. However, like the sigmoid, the softmax, which is a variation of the sigmoid, has the issue of it can get stuck during training, and then the gradient becomes very hard to pass by this last layer. So what we can do is to use the linear activation function and then use the categorical cross entropy, giving the parameter, which in Keras, by definition, does the softmax in itself. It's mathematically identical, but this gives a much faster convergence, and it avoids the minimum getting stuck. Then we just have the fitting, printing of training and validation loss, which these are pretty standard. And then here we can measure the accuracy using the Bratz categories, which is one for the whole tumor, one for the core part, which is label 2 and 3, and one for the active part, which is just label 4. And here you can see that using a very simple neural network, I can get this kind of distribution for dice scores for the 4 labels, which are quite high. Now, another issue that you need to keep in mind is that we define the model that works on single slices. What we need to do, however, when estimating the dice score is estimating it at the patient level, not at the slice level. By the way, most slices will be empty. So what we need to do is to get our initial data set before reshaping that and processing, in this case, one slice at a time, stack them together, and then compute the dice score of the whole patient. Here, as I always recommend, take a look at the results, a really visual look at the results. We are working with images. And here I'm plotting this is the predicted segmentation with as compared with the true segmentation, which is the contour. I use this strategy, and in this case, we can see that it works extremely well. But in general, for a patient with large lesions, this is a pretty good algorithm. Now here, I leave you lots of things to think about. There are multiple possible strategies to improve that. This is the most plain vanilla segmentations that you can come up with. And the things that you can reflect about is, are the number of classes equally represented, especially the background? And the background, by the way, is not one kind of background. There is air, and there is brain. And brain, by the way, it can be white matter, gray matter, CSF. So you could help the net. If you provide the segmentation, you can help the network in learning the appearance of the normal brain. Then, can you perform data augmentation? Then you can optimize the network architecture, of course. And 3D neural networks take much higher memory requirements, but sometimes you can work around that. This is what I was saying in the first part. You can perform reinforcement learning by requiring the algorithms to learn other non-clinical of interest part. Or another technique that was popular, I was about to say years ago, but because this field evolves so rapidly, is working with deep supervision. So you can train a second network that from the deepest layer predicts the presence of the lesion in the slice. And in this case, you're making sure that the information about the presence of the object that you want to segment is being transmitted down to the deepest layer. So that's it for the segmentation. And the last part of this notebook is an example of how you can do in TensorFlow a super lightweight in terms of computational resource, yet effective image augmentation. And in this case, what we want to do is, what we decide to do is 3 types of modifications. We have the translation, we have the left-right flipping, and the scale variation. So now for the translation, to use as little computational resources as possible, instead of interpolating the image in a new range, we just roll the array of an integer number of pixels, of a random integer number of pixels. And of course, we do it only on the first and second dimension, which are the ones related to the XY direction, and we don't do any rolling on the channel axis. Be sure to remember to also roll the labels, because otherwise it will be, you are giving some blurring, the network will learn some blurring, and that's something you definitely don't want. Then we have a flipping, because our brain are, at least at the visual level, are symmetric from left and right. They actually don't work perfectly symmetric, but whatever. And so you can flip along these axes, and so the network will learn some extra features this way. So, sorry, it will learn not to focus on certain features, on recognizing single patients more easily. As you notice, we are flipping only along one axis, the axis 0, and not along the both axes, because, of course, front to back isn't the same. Now, as you can see, and as I've told you in a previous lecture, this is definitely something that the augmentations that you can perform are something that you are putting with your own, based on your own experience and your knowledge about the data. Is not something generally easily generalizable. Like probably for broken bones on arms, that's something you can flip, but on a CT image of the thorax and of the abdomen, you cannot flip left to right, because the liver is on the right, the heart is on the left. So that's, I mean, the network will learn to segment anyway, but it will not do any help in generalizing. And finally, I've stated at the beginning that I was scaling images with my own function to bring them in a common range, but given that this was arbitrary, I'm multiplying the image randomly by a random number with a standard deviation of 7 with a mean of 1 and a standard deviation of 7. So we are putting a plus or minus 10% scaling jittering, so that, again, the networks learn to be robust to differences in scaling. We can see how I did it. Our initial scaling, first, I segmented at the first percentile because the error is 0. And then I just scaled by the mean of the whole patient. Again, this is something that I'm doing at the patient level, not at the slice level. And OK, so do you have any questions about segmentation or techniques to augment the data set? Now, remember that if you have very large data set, augmentation will not impact very much, but it can still be relatively useful. OK, if you don't have any questions about that, let me. Okay, medical imaging. Let me... Quello che ho modificato, cazzo. Okay, let me give you some details about the projects that that you will need to present at the exam. Generally, I require people to work in groups to do more comprehensive projects. Ideally, generally, the groups were made of 3 to 4 people. The groups can be smaller if if someone needs, but I don't want the project to to require too much time to anyone. For justified reasons, you might have a larger group. I will not evaluate the performances, of course, but the details on implementation. So how you pre-process the image when needed, which strategies do you use to evaluate your performances, if there are some checks on the robustness of your algorithm, if you use any special tricks, either computational or practical, to improve the stability of the results. Of course, clever implementations will be appreciated, and you can freely use any of the following. Sorry, so you can freely use either radiomics, uncrafted tools, or neural networks. Generally, the most popular choices has always been neural networks. Now, remember, you are free to propose your own project if for any reason you are interested, you have your own data set, you are working on some other projects. Otherwise, these are the databases that I can share with you and that I've already partially pre-processed. And the first is the ADNI database, the one about Alzheimer's dementia. And for this data set, I have 107 Alzheimer's disease patients with MR, 26 also have PET images. These are the ones that I have already pre-processed. Probably if you go on the webs, on the database, do your own data cleaning, the database matching, you can get a bit more. 65 mild cognitive impairment subjects with both PET and MR. And I also have a CSV file which tells for each subject if they remained stable, and in case for how many years, or if they converted to AD and how long it took. Then I have 346 healthy controls with magnetic resonance and 139 also with PET. All of them have been aligned to the MNI space, so they've been already resliced, taken to the same pixel size and so on in a common reference standard. You can do the following. There are multiple exclusive activities. You don't need to do that. Of course, you are not supposed to do all of them. You can either try to predict the Alzheimer versus control classification using magnetic resonance, not from PET, given that I've already given you many ways to do that with extremely high accuracy. Or you can also try, maybe if you have more time or you really like programming using unsupervised method, try to recognize in the unsupervised representation the gender of the subjects in healthy controls. You can try to predict mild cognitive impairment conversion from PET images or even from MR images, but I will tell you that this is very difficult in terms of the information being there. So if you try that, So, if the task isn't that feasible, then you don't know if you're programming wrong or if the task is hard. And if someone asks, I can also provide the images in native space, the segmentation in different classes from MR, or brain region labeling from standardized atlases to be applied to the MR. Now, for the BRATS database, I can give you the full data set of 117 patients with 4 MR sequence. We've seen that. Probably, I guess the one that that you downloaded is already the complete one. And you can try different strategies of segmentation to see how farther from the baseline algorithm that I've provided you can go from that. This is the only task you can do on that database. Then there is the pneumothorax database, which we ended up not using during this course, if not for reading a single image. But there is online, well, not on our drive, but I will give you the link, the full data set of 11,000 cases, which, by the way, are relatively unbalanced. So the pathology is like present in 20% of the cases. And you can do a number of tasks here. You can either predict the pathology status or even try to recognize the demographics of the subjects using from the image itself, which is, despite what you could imagine, is slightly harder on this data set than on the MR data set for some reasons that are not clear to me. And or then the other option is, again, do the semantic segmentation in this database. For all the subjects that do have the pathology, there is a mask, a segmentation mask with representative status, and you can do this. You can try to automatically recover it from the images. And this is a task which is relatively hard from using non-AI-based methods. With traditional methods, it's almost unfeasible, while with convolutional neural networks is relatively feasible. Now, this is when the data set was published, it was considered state of the art. Nowadays, there are many commercial tools that are able to do that. So it's pretty interesting to see how the technology improved in this field. Okay, so this is it. So let me just show you the two repositories that I will link to, where you can choose medical imaging-related papers. One is the International MICAI Brain Lesion Workshop. The MICAI is the medical imaging convention of, sorry, I don't remember the acronym, but is one of the biggest convention in image processing for medical, the medical field. And they have this, workshop on lesion segmentation. So all their papers are mostly about how to recognize lesions in the brain. Glioma, well, they don't publish much on glioma nowadays because it's mostly a solved problem, the recognition of data. But there is also multiple sclerosis, which is characterized by lots of very small white spots, stroke, traumatic brain injuries. And like if you, each of these links is a collection to the papers of that conference. And like if you click on the first one, 2023, which is the last edition, you can find a selection of papers about different topics or related to brain image segmentation. And here in this collection, they mostly describe algorithms themselves for segmentation. So it's mostly on training strategies, dataset selection, I don't know, transfer learning, and all other strategies that they have. You can find some very interesting papers there. The other collection is a collection by the European Society for European Association for Nuclear Medicine, and they have a collection of papers about advanced image analysis in nuclear medicine, of course, given that that's their field. And they have a collection with some more than 50 papers. This is a much more medical-based collection, while the other one was more IT-based one. But it's you can find lots of very well done papers and some not as well done papers. And of course, you need to select from here one of the original articles and not, you know, like guidelines, even if they might be interesting to read, or editorial comments. Okay, that's just we'll just introduce the two data sets. I will post the links to both of them on the e-learning.